Alright, this problem I'm a little nervous about. I didn't find on my homework, and now I'm looking at it like, what the heck? Okay, determine the anchoring force required to hold in place the conical nozzle attached to the end of the laboratory sink faucet shown in this picture. When the water flow rate is given, the nozzle weight is 0.2 pounds. Good thing I'm reading over this. Call it that. 0.2 pounds. The nozzle inlet and exit outside diameters are 0.6 and 0.2 inches. Got 0.6 inches up here, 0.2 inches down here at the opening. And the axial distance is 1.2 inches. The pressure at section 1, up at this first green line, is right out here, 68 pounds per second, pounds per inch. Pounds per square inch. Okay, so we're going to consider the force required to hold this up. We've got the weight of the water, and we've got the weight of the force acting downward. Plus we got some other issues. Okay, the control volume is already indicated in red. So for this control volume, FA equals rho omega 1 squared This is the z component of the linear momentum equation. So we only want z. Because we only have movement and such in z. Nothing really going on x or y. I don't know what this w is. If I did, I would be able to explain what's going on here. We've got the density and we've got the area. So this is mass per length square, or length cubed. This would cancel it out to be only mass per length. Don't really know what this one is, honestly. Well, I guess we'll figure it out together. Plus the weight due to the nozzle. Oh, it should be, if this is weight, then that's going to be in force. So here we're going to wind up with a mass per unit length. And in order to get that to force, we're going to need unit length squared per second squared. So this is a velocity of some sort. That's right. It's the z component of this whole velocity vector. I'm sorry. I just was so used to seeing u and v. I didn't even think about w. So this is a capital W. This is actually weight plus P1A1. This is the pressure times the area, which will come out to be a force, minus P2A2. Alright, so okay, I changed the direction of this arrow is actually wrong. The arrow that I drew is actually corresponding to Q. This is a Q out. P2A2 should be producing something upward into the control volume. So what we have here is we have the density, which is, it's incompressible, so the density is constant, times a velocity. This is velocity downward. It's odd that they would do that. But apparently downward is positive the way they set this up. So density times velocity downward times the first area. And this is going to give us a force. I don't really understand how this is different. Okay, FA is, if we did FA plus all this mess, or rather minus, because, you know, it'd have to be negative to switch sides, then it should all equal 0. So we're summing everything in the down direction, and this has to be equal to the magnitude in the upward direction. I don't know if that makes sense to you. But if we had it on the same side, then what's going up minus what goes down equals 0. You know, that makes sense. We just moved all the minus stuff, all the down stuff, over to the right, so it became positive. Okay, so, dang it, why are you right there? Okay, I can't get to my eraser because of the way this recording program is working. So I guess I'll keep working. Alright, so we've got, this is some sort of weight. I don't really understand it, honestly. But it's like the rate of the weight, or normally when you're talking weight, you just multiply, when you're talking mass, you multiply the density times the volume. But we're talking weight, not mass, so we need a mass times an acceleration. And we get that through all this, through the velocities and such. Okay, so starting to kind of make sense. Conservation of mass says that I thought I changed you. There we go. Says that the mass flow, the rate of mass flow, is equal to rho 1 A1, and it has rho omega 1 A1 also has to equal rho omega 2, not omega W 2 A2. Because of these 2 points, it has to be equal, or else we're going to have some serious backup. We won't have a good steady flow. Another explanation of force is that it's the mass flow. This is this section right here. This is the weight portion of the weight of the water portion. This is saying this is the area in between these. This is the section of the control volume that has the water in it. So this is the water that is inside the control volume. We've got the velocity of 1 minus the velocity of 2. Seems like it's going to give us something negative, because the velocity of 1 should be slower. I don't know, we'll keep going, we'll see how this goes. Alright, plus the omega, and I'm going to go ahead and put in the 0.2 pounds, just because I keep saying omega, you know. It should be W, long class. Okay. Plus the pressure 1 times area 1 minus the pressure 2 times area 2. Alright, the different terms in equation 2, the different terms in this equation are calculated below. Alright, so you got mass flow is the density times the mass flow rate. This is given as 10 gallons per minute. Excuse me, no. The density is given as 1.94 slugs per feet cubed times 10 gallons per minute. I'm trying to write out minute there, that's crazy. Times 1 over 7.8, excuse me, 7.48 gallons per foot cubed times 1 over 60 seconds per minute. And this is going to give you 0.0432 slugs per second. If we look at our velocity, 1, that is our flow divided by our area. Very simple there. They actually calculated it all out, did all the conversions and everything. I'm not going to do that again because that's a waste of time for me. You can just go look if you're in my class, you can just go look up exactly what he did. And I'm focusing more on the